This is lecture 19 of CS47 Computer Organization Study. In this lecture, we'll study and learn about the multiplication digital circuit. Underlying assumption is this multiplication is for integer multiplication, not for the floating point. So, to understand multiplication operation, let's first review what we do for the decimal multiplication, right? Multi-number. It's basically we learned it paper pencil method. Just let's pick up some example like 2345 multiplied by, let's say, 1277, and we're doing multiplication here in this case. So what we do, if you remember, actually let's move this guy a little bit shifted towards the right. Okay. So what we do here in the decimal multiplication, we call this guy is your multiplicand, and this operand as multiplier, right? Multiplier. So what we do, we take each digit of multiplier from the unit position, first unit, then tens position, then 100 position, then 1000 position, and so on and so forth. We take each digit in the multiplier position from unit position towards the higher position and multiply that digit with the entire number, the multiplicand number. Okay, so we do like 5 multiplied by 7, which is like 35, and then we have carryover of 3, right? And then 4 multiplied by 7, which is 28, plus 3 is 31, and that means its carryover is 3 again, and then 3 multiplied by 7, 21, plus 3 is 24, right? And carryover is 2, and 2 multiplied by 7 is 14, plus 2, 17. So we write down 17 here, right? So essentially we multiplied 7 with 2345, which results in 17,415. Let's check again, like 5 into multiplied by 7, 35, have 3 in hand, and then 3 carry over 28, plus 3, 31, 3 carry over 24, 2 carry over, and 14 plus 2, 16. This is 16, right? Not 17. This is 16. So 16,415. All right. So similarly, we do for the other digit, but what we do is kind of omit the unit digit in the next part, right? We just place a X or space or blank, and then we carry out multiplication for the second digit of the multiplier, the tens position digit of the multiplier with the multiplicand. Now in this case, it will be same as your 16,415, right? And then, so this each step is, we can call it a partial product. I'll tell you, like, partial product is kind of more than this. I'll basically describe that in terms of when we do binary multiplication. But let's say this is a product term, partially each step. Let's take it that way. But partial product is basically two product values, two step, and that addition becomes a partial product by definition. But this is more or less your part. Let's call it a part of the product, not partial product, just to be clear on the definition. Now next line, what we do, we put two gaps, like one in unit place, other is 100 place, and then multiply the digit 2 with 2345, and which becomes like 4690. 4690, I think. 600. Is it true? 5 multiplied by 2 is 10. We have carry over 1. 4 into 4 into 2 is 8 plus 1 9. 3 into 2 is 6. 2 into 2 4. Okay, all right. Then the last one would be again, like, so we left 3 spaces now for the fourth line, and 1 multiplied by 2345. So we do 2345, and then we sum them up, right? So here in the summing up, we practically treat this x as 0, isn't it? So I can as well replace this guy with zeros. Right? And then we sum it up. So this column would be summing up to 5, this column would be 6, this column would be 5 again, this column would be 18 plus 6. 18 plus 6 is 23, carry over 2, 18, 19, carry over 1, 9, and 2, right? And here, if you kind of noticed, there are spaces also with respect to when we are adding up 2, and we kind of assume that there are zeros upper hand as well in the upper rows in those positions. Like this. So there are zeros introduced in the right hand side and zeros introduced in the left hand side as well in this whole picture, which we kind of assume implicitly that's blank, treated as zeros, but zeros are really there. So this is the decimal multiplication, right? Now we'll see about the binary multiplication. Similarly, like, let's take two binary values, two values represented in binary format. One is multiplicand 1000 and multiplier 1001. Now in this case, what I would like you to remember or know that if you multiply anything with 1 in binary, any binary values with 1 binary, it becomes that value. Just similar to if you do a decimal 1 multiplied to anything, it's become that value. And if you multiplied any binary pattern with binary 0, the result is 0. So for us, this is binary multiplication is kind of simpler in form. We don't need to remember different combination of multiplication as we want to do for the decimal multiplication. Binary multiplication, if you are multiplying something with 1, it is that value. If it is multiplying something with 0, multiplication value is 0. Simple. So what we do, we start like the paper pencil method as a first bit of the multiplier and multiply with the multiplicand, and that becomes, because we are multiplying with 0 with 1, so it is 1000, right? 1, not really 1000 in a decimal, it's a 100 as in binary. And the next one would be 4 zeros, but I shift it 1 bit, just as we did in the decimal, and assuming this LSB is of an implicit 0 staying there. And the next digit, we do the same thing. We increase the spacing from the right hand side, and we insert 2 zeros, implicit zeros there. And then the next row, it is basically at the right hand side, we have 3 implicit zeros, and result is 100, which write it by shifting one place. from the previous row, right? And we add them up, all the columns. We start adding them up, and whatever that addition become is my result. Now let's review this process in a little bit different way. All right, let's say I have multiplicand and multiplier stored in some 8-bit storage and 4-bit storage. Okay, first of all, one thing, you need to know that if you are multiplying n-bit values, your result always going to be 2n-bit. Okay, so you can say that, hey, I have two 4-bit values and I should have get an 8-bit result. Look at this result, it's 7-bit, right? Isn't it? 1, 2, 3, 4, 5, 6, 7. What about that, right? Okay, well, you add 1 0 here. So your result is really in this multiplication is 0 1 0 0 1 0 0 0. So 4-bit multiplication results is always going to be your 8-bit result. Sometimes on the paper pencil method we don't show all the bits, especially all the bits at the left hand side, because that does not impact the ultimate value of the representation, right? But always know those zeros are there by theory. You are multiplying, in this case, two 4-bit number, your result ought to be 8-bit. Okay, with that light, what we can now want to show that we are storing the multiplicand in an 8-bit storage. Remember that we talked about register. Register is one kind of storage, and we deploy a 8-bit register to store 8-bit inside it. And we deploy a 4-bit register to store multipliers 4-bit. Now what we do, we take the first bit or LSB of the multiplier, let's say, and passing the entire multiplicand, 8-bit multiplicand, through some multiplier circuit. Somehow we can do multiplication, and the result being written as a partial steps. So 0 0 0 1 0 0 0, right? So that becomes your multiplication result from the first bit. And then what we do, we right shift the multiplier by 1 and left shift the multiplicand by 1. Okay, so we right shift the multiplier by 1 and multiplicand is shifted left side 1 bit, and then we do the next step multiplication. So as if we are taking the multiplicand and shifting 1 bit position. This is kind of mimicking what we do on the paper pencil method, more like an implicit way, but we are kind of shifting. When we are writing the result, we shift one column towards the left hand side. So that's exactly what we are doing at this point. We left shift the multiplicand, and then multiplier gives, now it is your first bit. We are still looking at the first bit of the multiplier, and since it is 0, our result is all 0. We write them in a 8-bit form. Okay, so here the gray zeros and gray bits and the black bits are kind of to show you the equivalent or analogous to your paper pencil method. What we do for the paper pencil method, but what electronically we are doing here. We are actually dealing with all the 8 bits here. Now we are doing a partial sum. So what we don't do in the paper pencil method, we delay our summation till the end, till we compute all the rows, and then we sum it up. In the electronic method, we sum at each step. Whenever two partial or part of the product is available, we add them, and that becomes a partial sum or partial multiplication result. Okay, so we add them, and my addition result becomes this. Then we right shift the multiplier by 1 again, left shift the multiplicand by 1 again. So if you notice what we are doing with multiplier, instead of looking into each bit at like at a different position, like okay, LSB first and then bit 2, then bit 3, then bit 4, instead of doing that, we are kind of fixing our eye on the LSB position only. We are picking up bits from the LSB position. What all we are doing, shifting out the multiplier as a right hand shift, so that we are making use of that LSB1 fixed position to look at this bit and use that current bit in the multiplication at that step. And that absolutely works because instead of looking at bit 1, bit 2, bit 3, bit 4, etc., we are looking fixedly on the first bit, LSB, call it a bit 0 or bit 1, doesn't matter. The LSB, we're looking at that position and shifting out the multiplier with a right shift. So each step we are actually equivalently looking into the next bit of the multiplier. So why are we doing it? Because it is easier to implement on the electronic circuit. It is rather difficult to keep the multiplier fixed and kind of having an observation or scoping mechanism in the electronic to like carry over, like look into first bit and second bit and third bit. It is hard to implement. Then we look into one fixed position and shift in or out some bits. So this fixed bit position, this purple one, is kind of, you can think of is treating as a window, like you are looking through that window for a bit, and your multiplier is constantly going out of the scope towards the right, so that you are poking into or probing into higher bit one step at a time. Okay, higher bit one step at a time. So we do that, and again partial like that step product comes in, we do the partial sum, and then we do the similar shift, we do the partial sum, and final result, right? So this is the last bit we are done, and this becomes my final result. And in this case, you see we actually got a result 0 1 0 0 1 0 0 0. So that's the behind the scene multiplication operation, and this exactly implemented in the hardware. We'll see that.